The topic of my talk is Future Through Sustainable Innovation, connected with a plea for a new renaissance for Europe. Actually, that is also the slogan of our presidency now at the European Academy of Science and Arts, and it is on the background of a recently published book. This is the German title, and I hope it will also translate it into English. And the title is exactly the title of my talk, Future Through Sustainable Innovation, with the subtitle In the Competition of Worldwide Political Systems. So the key to a successful strategy of mankind, from my point of view, is sustainable innovation. Now I will start with some remarks towards the European Academy of Culture and Innovation. Then the question, what are innovation portfolios? And then I will consider special innovation portfolios, namely of energy, technology, and digitalization and AI. And finally, future through sustainable innovation. Let's start with these first remarks towards European Academy of Culture and Innovation. And here I like to start with this historical hint. I like to remind you of the first Academy of Europe, which was founded in the 4th century before Christ, near to Athens, founded by a philosopher, Plato. And the students in that time were educated in the mathematical disciplines already, in logic, physics, and ethics. And that is also the Greek heritage for Europe nowadays. That was embedded in the Greek polis, and that means in the framework of ancient democracy. Now, and as you know, in the 14th, 15th and 16th century, there was this wonderful period in Europe called Renaissance, and in that time the school of Athens was glorified as a paradigm of philosophy and science. And here is this famous picture of Raphael, which you can admire in the Vatican nowadays. And perhaps you remember here in the center there are these leading two philosophers of the ancient time, Plato and his student and former and later also famous philosopher and scientist Aristotle. And on the left, on the right, this distributed over the following centuries all these famous philosophers and scientists in that time. By the way, here on the right, the great representatives of the mathematical sciences, the astronomers, the mathematicians, here busy with their instruments. And in that time of Renaissance, people became also fascinated by new discoveries and inventions. Ingenious artists tried to unify science, arts, and engineering, and that is the time of Leonardo da Vinci. And I think that is the heritage. By the way, it reminds me, yesterday we discussed about STEM nowadays, science, technology, engineering, mathematics, or in the German tradition nowadays it is abbreviated MINT, mathematics, informatics, natural science and technology. And I think that was also born, these ideas, in the time of Renaissance. And in that tradition we feel in our academy, the European Academy of Sciences and Arts in Salzburg here. And the idea is nowadays, especially stressed in this presidency, to transform this assembly of recommended scholars into a working academy. And therefore we started with certain expert groups. First expert group dedicated to a challenge nowadays in Europe, digitalization, artificial intelligence and its societal impact. All these expert group on environment, climate and energy, or in general consideration, innovation, research and education. And in these activities, of course, the goals of humanistic education must be incorporated. And in the following, I will consider what I will want to call innovation portfolios. Why portfolios? You know, portfolio is a term in economics, and it is used in the stock markets. Now, the idea is the following. It is a warning for the risks of what is called in economics path dependence. People tend to prefer not to leave cheap and hitherto successful development paths than to focus on new innovation. And this formation process of a path dependence is illustrated here in this graph with these different stages. For example, in Germany, you remember in car industry, and I learned here in Slovakia, you are also engaged in car industry. In car industry, people were very successful for decades in diesel technology. And then, of course, you earn much money with diesel technology. And therefore, especially in Germany, the CEOs and all these experts, they hesitate to change to a new technology. Because why should we do that? And that, of course, was a great danger, as you know, in competition with China now, because they feel free and jumped to this new technology much earlier. So path dependence is a great challenge. By the way, it is a term which was introduced in economics by an American economist, Brian Arthur, the beginning of the last century, and Joseph Schumpeter. Schumpeter is a famous Austrian economist. Path dependence was recently dramatically demonstrated, I think, when even in politics and economy, when some political and business leaders brought European countries, especially my country, Germany and others, into the energy policy dependence of essentially a single country with fossil energy. And you all know which country I mean. That was Russia. Russia with inexpensive gas. And there was a dangerous path dependence there. And therefore, technologies, I think, especially future technology, can be considered such as at the stock markets. They are like shares. They are bets on the future, such as at stock markets. And you all know a good portfolio. A good portfolio is characterized by diversity and variety in order to avoid the risks of path dependence, to be robust and resilient and make a good long-term cut despite all future crises. So an innovation portfolio here, innovation is composed of basic technology, bridging technology and future technology, and that is always in movement. For example, coming back to the diesel technology. The diesel technology, it was invented in Munich at the Technical University by Rudolf Diesel, a pupil of one of these famous professors in that time, Carl von Linde. And the diesel technology in the end of the 19th century was a future technology. But then in the 20th century, it became for nearly 1 century a basic technology. And nowadays we observe its limits. And we will give up it because of its harmful effects to the environment. So we must carefully analyze what is going on with basic, bridging and future technology. This is a graph to illustrate the relations between basic, bridging and future technology. And now at first let us consider an innovation portfolio for Europe of energy technologies. And the idea is in the end to have such a kind of good portfolio with diversification and with respect to innovation with a sustainable future for Europe. And here for this application you see again the basic technologies that will mean fossil, renewable, nuclear technology, then the bridging technology which is now coming up with hydrogen, and the future technology will be fusion energy. And of course basic technology of energy is nowadays fossil energy. A lot of European countries still must rely on that. Also, we know the harmful environmental impacts. And therefore the request is nowadays to replace step by step these fossil energy by renewable energy. And we discussed already about that, solar, wind, ocean, water and so on. But the question arises, is that sufficient for Europe? And therefore always also a basic technology is nuclear energy. And you know the vast majority of electricity from nuclear power is nowadays produced by nuclear fission of uranium, plutonium in nuclear power plants. And from an environmental point of view that is fine, because you avoid these harmful effects for the environment and reduce carbon emission. But of course we all know there are severe risks connected with nuclear energy. For example, the risks of radiation or the problem of nuclear waste storage. And so you also know that some few countries, Austria, Germany, I think also Italy, they gave up nuclear energy. But my personal view is European, and we must be cautious, because in Germany recently these old plants which were introduced in the 70s and the 60s, they were abolished. But research is in movement, is going on, technology. And perhaps you know in England and in France they are planning and even are already constructing these small plants, and with decreased risks, and concerning the nuclear waste storage, there are reflections on new technologies concerning the transmutation of elements and with radiation, and recycling of the fuel rods. And so technology is in development. These are not the final solutions of these problems, but I think it would be a great mistake to give up research and investment in this technology. And so I think without any doubt bridging technology now to the future, before we will have fusion technology, is hydrogen energy. Only water vapor is produced during combustion, and no environmental harmful substances and released, and hydrogen is also easy to store, and there is enough of this stuff in the world. But we must produce hydrogen. It is not isolated, cannot be found isolated in nature. And so nowadays there are degrees of this technology, with more or less advantages, and that is illustrated by color names. For example, gray hydrogen means the production is made possible by coal and gasification processes, and that is of course not a great advantage with respect to renewable energy. And the best solution would be electrolysis with renewable energy, and therefore it is called green hydrogen. And then, of course, on that way, once day future technology such as fusion energy. And that may be the ultimate solution of our energy problem. You know, we will then bring the energy production of the sun to the earth with these kind of stellar nuclear synthesis, transforming the lighter elements into heavier elements with the release of energy. And I think this way of future technology is also very exciting from the point of view of innovation, organization, namely ITER in Europe. More than 35 nations are collaborating here in order to build up the world's largest tokamak. Innovation, organization can be learned here across all nations and political boundaries. Now let us consider the same idea, innovation portfolio for digitalization and AI. And so in the same way, I will show that we can consider basic, bridging and future technologies here. This is again illustrated here in this picture. And basic technology will be the basic digital computing. A bridging technology is what is nowadays called machine learning. And then future technologies, quantum and neuromorphic computing. I will come back to that in some minutes. So in the beginning, there was this guy. I mentioned him for several times. By the way, he was always also a famous runner. I mentioned it this morning, and if I would be informed about the background here of you as the head of this center, then I would have chosen a picture of Turing as runner. Now, anyway, in 1936 already, he came up with the first, he was a great mathematician, actually, he came up with the first logical mathematical definition what a computer is. And the digital computer, the essential idea is a strict separation between a processor, which is able to read and to write and to print and to control the digital process, that is the processor here, and the storage. And the storage is here in this concept of him a simple tape and with these stored digits here. And that was later on technically realized some years later in the 40s by the first digital program-controlled computers, the so-called von Neumann computer. And therefore, nowadays we speak about the von Neumann architecture, which is still realized in all kinds of digital computers. That may be your smartphone, that may be a supercomputer. It's the same principle. And then also Turing in 1950 came up with the first definition of what artificial intelligence is. And artificial intelligence, in his suggestion, is nothing else than a kind of simulation game. He even calls it simulation game. By the way, you know, Turing was this guy who encoded the German Enigma. And Churchill said, without these code breakers near to London, the World War II would take at least 2 years longer. And that would be another story to explain how this idea of Turing, of simulation, of digital simulation, was a basic of his key to encode the German Enigma, the coding machinery of the German military in the Second World War. Now here the idea of artificial intelligence is very easy. It is illustrated here. The idea is his suggestion, let us call a system, a computer, intelligent if its answers and behavior cannot be distinguished from a human by a human interrogator who is communicating with both hidden behind a wall. That is the main idea of the famous Turing test. And in the Turing test, at first, the idea was in the 50s and in the 60s to simulate logical thinking. That means the idea to bring our thinking to rule-based formal systems. And that was the basic idea for the first so-called expert systems. The idea was to represent the knowledge of a physician or the knowledge of an engineer in a rule-based way. If the premises is fulfilled, then something must be done. And in this logical way, for example, to derive from the symptoms of a physician to conclude the disease and things like that. And that was actually fine, but in a very restricted way, because people realize a human expert and his ability cannot only be represented in textbook knowledge, in rule-based way, but it depends on the background knowledge in an intuitive way. And how can we represent that? That would need a lot of data, and therefore in the 80s, 90s, the idea came up to make a paradigm shift in AI from the logical orientation to statistics, the statistics of big data. And in that time, computer technology was become more and more powerful, and so the machinery was able to do this kind of statistics. And that was then called machine learning, and machine learning is a modern version of AI nowadays, and it is realized by brain-like architectures, computational systems, which are also called neural networks. And here are some of these architectures. Here in the graph you find these nodes, and they are representative in the living brain of the neurons, and these arrows represent the synaptic interactions. In the graph, these arrows are weighted by numbers, so-called weights, indicating the intensity of the synaptic signals. And such a node is said very similar to the brain to fire or to generate a bit or a signal if the sum of the weights here of the neighbored neurons is larger than a certain threshold value. Now, by that you get a stream of signals, a data stream, which is led through this architecture, and which, by the way, is similar to the neocortex of the human brain, which also has 4 or 5 layers. And then this data stream is triggered by learning, so-called learning algorithms. We can distinguish certain kinds. I will not go in all these details, but supervised learning only means that at first you must train this network by a kind of prototype. For example, a face. A face is statistically expressed the distribution of pixels. And by adjusting these weights, this is is trained to the machinery, and then these networks are actually able to recognize the trained pattern among a huge number of other perceived faces. And this kind of application is already used since many years by police hunting of criminal persons by their faces. Reinforcement learning means that was also used by the engineers for a long time, means that the algorithm is able to improve its own solution strategy by rewards from the outside, and deep learning only relates to the depth of the network. That means the number here of these layers, which is illustrated here. Only 4 layers, very similar to working in the human brain. First layer, only colored pixels are distinguished, then they are connected in edges and corner, then on the next level partial faces are recognized, and then finally the whole faces. So actually, these neural networks, what can they do? Pattern recognition. Pattern recognition in big data. And there were a lot of breakthroughs in the following time here in medicine. This network here is able, with application in breast cancer, to distinguish the distribution here of cancer cells here in red, distinguish them from the normal lymph nodes here in green. And it is an example of supervised learning, because at first the system was trained with the criteria of cancer cells. And then in 2018, Google and other companies came up with this kind of multi-layered neural network, which is actually able to analyze proteins. And you know, the proteins are the basis of life, and proteins from a chemical point of view are built up of amino acids as building blocks, and here a change of amino acids, and represented here by these letters, and the machinery is able to check very carefully this chain in order to detect deformations, that means deviations from the normal shaping, from the normal folding of the proteins, because that may be at a very early stage the beginning of tumor growth. And by the way, the acceleration, the enormous acceleration of production of medicaments and vaccines in the last year during COVID crisis would not be possible without these kind of IT and AI algorithms. At the end of the last year, these chatbots, which came up with amazing applications, ChatGPT for example, these are neural networks, not 4 or 5 layers, you remember, such as the neocortex of the human brain. These practical, real-world neural networks nowadays, they have thousands of these layers. They consist of millions of neurons and billions of weights. And such a kind of neural network is a ChatGPT, and you know these amazing results. Some people are horrified by that, because these networks passes the Turing test, which I mentioned before. It's able to simulate and to reproduce all kinds of texts. You have some desire, and then the chatbot is able to write the text for you, even text for examination at the university level, at least in the social sciences and in the humanities, on the basis of large language models. So from a technological way of point of view, this kind of networks are overcoming, you remember, the restriction of the first approach of AI, rule-based, and the background knowledge. And therefore, people nowadays are horrified by that. Some people are delighted, the researchers, of course. So let us have very neutrally short view in the machine room. What is going on? There is no consciousness or things like that, like in a human brain. There are only two kinds of algorithms which are mentioned before. First, the supervised learning algorithm. That means the system must be trained with a certain amount of data. And by that, we should know the limitation of the machinery. What is not stored cannot be known by the machinery. And the second application means this kind of reinforcement learning. That means the system is able to improve its solution. You can make your own experience with a chatbot. And if the chatbot is giving you an answer and you are not satisfied by that and you criticize the chatbot, then the chatbot will start with a new answer. And so step by step it is improving its solution suggestions, but there is no guarantee that in the end the best solution is given. And by that you can also test the limitation. That may be that at some stage the system will say, oh, I don't know. That is also the chatbot. So in the end it is a statistical machinery again, and that means from a statistical point of view the system is computing probabilistic expectation values of data and digital simulation, and therefore I call them statistical or stochastic parrots. And the problem are not these parrots here, the problem is the interaction with us humans. And perhaps you recognize this lady here, the former chancellor in Germany, and that means the politicians are also influenced by that. Now, digitalization nowadays does not only mean a single chatbot or a single neural network or single computer, but it means nowadays a huge global network since the 90s that was the internet. And that is illustrated here on the left. And the internet was actually a network supporting human communication. And then some years later, a new technology came in that is here indicated by this plus, and that was sensor technology. That means the things are equipped with sensors in order to communicate with one another. Not only humans are communicating, but also by codes, things, and therefore it is called the Internet of Things. Not only our smartphones, but also cars, robots, aircrafts, and even some houses, perhaps this house too, now or in future, organizing itself by kind of self-organization, electricity or the heating problems, whatsoever. So the Internet of Things, and this picture should illustrate perhaps the future. What will be the future of the Internet of Things? I think all these different kinds of infrastructures which are already realized will grow together, maybe in order to illustrate here in this metaphor, such as a kind of superbrain which is spreading all over the planet Earth. And here on the right and left, perhaps you can recognize the catchwords of the digital infrastructure which is already realized nowadays. For example, the smart cities, that means intelligent networks of mobility, or the smart grids for optimizing energetic network, are very important. For example, with respect to the car industry here in Slovenia or in Germany or elsewhere, the Industry 4.0, it's sometimes called, or the industrial internet. That means that the things in the factory are equipped with these analog and digital equipment in order to communicate with one another, in order to automate production and trade step by step. Or in the financial aspects, these global financial networks, the stock markets nowadays would not be possible without this digital equipment. There are nowadays even algorithms in flash trade which are much faster than the human brain, and that of course is very dangerous, because then there is a danger that decisions can be made by the algorithms and we become aware to that when the suggestion is and the decision is done. Or the health system with the digital equipment, or in time of wars nowadays we all know that the military equipment would not be possible nowadays without the support of IT and AI. Now, future technology. We must not forget that this kind of digital global equipment is nothing else. Remember, the beginning with Turing is nothing else than simulation, digital simulation. Digital simulation on a von Neumann computer. And that has severe problems. Because remember my remarks on the von Neumann or Turing architecture. It is the basic idea that there is a strict separation between a memory and the processor. This is illustrated. The basic architecture of every kind of digital computing until today. And that means with an increasing amount of data, that all these data must be pressed between these two units, and that is called nowadays the von Neumann bottleneck. It is like in a ketchup bottle. You know, there is the bottleneck, and the ketchup is now the data, and the data is becoming more and more and must be pressed through this architecture, and that needs a lot of not only time but especially energy. And in some years the major part of energy consumption on this earth will be in digitalization. And on the other side here again this graph to illustrate the architecture of the human brain. And the human brain is amazing, efficient, energetically. Only 20 watt. With 20 watt, all these amazing activities of us is realized. And one of these reasons is that the architecture of the human brain is completely different to a digital computer. No strict separation of processor and memory, but these two functions are realized in each synapse. Yeah? No separation, but the synapse can sometimes be a processor, operate as a processor, or sometimes operate as a memory. And there is not only one synapse, but there are billions of synapses here, so there is no danger of a bottleneck. And you can measure the energy which is necessary for a simple computational device in a computer and in the brain. In the computer, a simple, the so-called Mac device, needs 1 picojoule. Pico is 10 to minus 12 joule energy. The brain only 10 to minus 18 joule. So there is a difference of which supports that the brain is 1 million times more efficient than a modern computer. And that motivates nowadays the people to look for new hardware. And that is meant by neuromorphic computing. hardware which is oriented to the brain. Of course, we will not be able for a long time to realize it by tissue, living tissue. That means the biological brain. But the architecture of the biological brain can be realized in well-known materials, silicon materials, and that means nowadays neuromorphic computers. I underline that because I'm engaged in this development since many years. I cooperated at least since 2000 with the inventor of the first kind of unit which is able to integrate the processor and the memory function. These are the so-called memristors. That was Leon Schuer from Berkeley, a computer scientist and electrical engineers. And in 2013, I wrote a book with him about that. So that this functionality is realized in silicon by electronic circuits. I will not go here in the details, which are able to simulate these architecture in hardware. And nowadays, by that background, I'm in the advisory board of the German Ministry of Research for, it is called future innovation or future technology, a future cluster, which is called AI neuromorphic systems. And it is situated, by the way, at the RWTH Aachen and the research center in Jülich. So the idea is in cooperation with industry, concerned industry, to realize this new kind of hardware. And I will not go here further on in the details. There are also ideas to realize it with photonic circuits. So I think this is on a good way for a good solution of especially the energy problems. And by the way, from a mathematical point of view, this kind of analog computers will also be able to solve problems which cannot be solved by a digital computer. That is an amazing result by mathematicians in the recent years. And then another future technology is a quantum computer. You all know that. These are the two prototypes from 2019, introduced by IBM and Google. But these prototypes are only able to solve very special problems. So what we miss until today is a general purpose quantum computer, such as a general purpose digital computer, which is able to solve any kind or many kind of problems, and not only restricted like these prototypes to a certain problem. And the basis of that were, perhaps you know that, were deep insights on in quantum physics, and for example the idea in quantum physics of a so-called superposition. That means comparing it with the von Neumann architecture. In the von Neumann architecture, you are enforced, for example, to elaborate a sequence of bits, bit by bit, one after another. That's the von Neumann architecture. But here, the quantum physics opened a new possibility, namely you can collect a sequence of bits, perhaps billions of bits, in one package. That is a so-called superposition, and you can applicate the computational device to this so-called superposition of many bits. So that means enormous acceleration of computation nowadays. And again, by this technology, and that can at least nowadays mathematically be proved, there are problems which can be solved by a quantum computer in operable time, which is not possible by classical digital computer. And another famous property of the quantum world is the so-called entanglement. And entanglement means, perhaps you know that already, means that far distant elements, for example photons, in a far distance can be brought into a common quantum state. And that opens, Anton Zeilinger and others were engaged in the realization of these kind of entanglement. That opens new avenues for communication, quantum communication, and in the end, the perspective of a kind of quantum internet, again with enormous acceleration of communication. And by the way, you know that here in the neighborhood, Austria, that was for special cases already technically realized. And there is a nation which is engaged in these technologies, and that were former students of Zeilinger who are now the heads in China. And so Shanghai and Beijing and other cities are already entangled, and the quantum internet is growing there. Now, we are nowadays in a period between the so-called second and third generation of quantum technology. The first generation was in the 80s. You remember that was a time when the laser technology was introduced into industry. And then the second generation means these prototypes, which nowadays are already realized with a special solution of problems. And then the third generation would mean the introduction of a general purpose universal quantum computer, and that would need more than 1 million quantum bits. That means the superposition which I mentioned. Now we are between the second and the third generation, and that in an abbreviation, this time interval is called NISQ. And NISQ is the abbreviation first for noisy, because the number of these quantum bits, which are technically nowadays realized, are not sufficient to correct the failures of decoherence and perturbations. And intermediate means that the number of these qubits, quantum bits, is insufficient for the universal quantum computer. So in end, to close this consideration of IT and AI innovation portfolio, we aim again on this kind of portfolio, and considering all these possibilities, they should be considered in Europe for a good solution of IT and AI solutions. Now, at least some remark concerning the future through sustainable innovation portfolio. What means sustainability in this context? We all know we are living in the Anthropocene. Anthropocene means, and that is illustrated here in this picture, that our planet Earth does no longer only depend on natural factors such as climate, energy, water. That was the situation before mankind came up. But nowadays, the whole activity and dynamics here on our planet also depends on all kinds of factors of human civilization. The growth of our industry, population growth, our social problems, and they are coupled here by these feedback loops with one another. And that is a typical picture from a mathematical point of view of a complex nonlinear system. And we know, I'm engaged in this kind of research of the complex system since many years. We know this dynamics is highly sensible to global to global effects. That means local perturbations in this kind of dynamics can lead to global destabilization of the whole system. And therefore, concerning especially economy, we must give up what is called the linear economy in this kind of non-linear world. Linear economy is illustrated here, starting with raw materials, and step by step only residual waste is produced without considering what is going on with this residual waste later on. We must incorporate here recycling and these feedback loops in order to aim at what is nowadays called a circular economy. And I'm engaged and was engaged in research on that. This is a book of the Technical University of Munich, and I was especially responsible for the digital equipment of such a circular economy. And circular economy in the end could not be realized without these digital infrastructure. So in the end, these are my last slides. We are on the way, I hope, towards sustainable, responsible innovation. And that means in the end, we have to realize the decarbonization. That means renewable energy, nuclear energy, alternative fuels. And on that basis, sustainable development, which means energy efficiency. Remember the neuromorphic computing, for example, increased flexibility and circular economy, and then digitalization in a sustainable way can be realized with the Internet of Things, artificial intelligence, and we all aim at sustainable innovation. And that in the end means that sustainable development goals must be integrated into technologies and societal infrastructure. And this is a survey on the Sustainable Development Goals, the SDGs of the UN. And you see some of these points are obviously related directly to sustainable innovation. For example, here, number 9, industry, innovation and infrastructure, or here, sustainable cities and communities. And this is my last slide, coming back to the beginning, my plea for a new renaissance. That means for Europe, sustainable innovation to guarantee the welfare of this continent, and that is the Greek heritage of Renaissance, namely it should be embedded in a political democratic order. And I think there are at least 2 arguments to support the plea and the request for democratic order. The first one is simply an economic demand, because democratic order means separation of power, and it especially means the independence of court and legal decisions. And I think that is an attractive and reliable argument for the markets. And because markets are always involved in legal affairs, and here in a democratic state, that is at least the ideal. You can rely on this. You can rely on these decisions. And last but not least, to defend our European way of life with the human rights in the center. And here, this is the festive declaration of the human rights during French Revolution, and nowadays it is in the center of the European constitutions. Here the EU Parliament. So with this picture and impression, I like to close my presentation again with a plea for new renaissance, sustainable innovation with democracy. I thank you for your attention.